Welcome viewers. In this video we are going to do design of substation gantry foundation in Eurocode. This is a stage 6 out of 7. In this we are going to discuss about punching and one-way shear. These are the various design stages which we had seen some of in that. In first one is an overview of calculation we seen in the first part. In the second part we have seen the foundation and soil parameter load and load combinations. Third is a stability check. Fourth one is an anchor bolt design. Fifth one is a design of bottom slab. Sixth one is this is a video. In this we are going to look the punching and one-way shear, and finally we will be looking the design of pedestal in the 7th stage. Now let's look into that Excel calculation which is prepared for demonstration. You can see an Excel sheet on the screen, so which will be demonstrate about the punching and one-way shear. So first we need to calculate the effective width parallel to X and Y. So for that we need to take a measurement which is half of the distance of effective thickness of bottom raft on both the side of the column. So that should be measured from the face of the column. So the total length, effective length shall be T effective divided by 2 into 2 times, because on the both the side we are having the same width of the strip which are subject to the punching shear, plus the column size B. You can see on the right hand side picture the plan which is explaining about that. So the punching shear will occur in the circumferential strip of the column face. So you can see this T and TRC are the column which are subjected to tension or compression or only compression or only tension according to the bending moment. So the effective strip width we need to calculate as TEF divided by 2 into 2 times TEF divided by 2 plus L or B according to the direction of the column. So in the elevation view also you can see this strip around the column are subjected to punching shear or two-way shear. So now the effective width parallel to X or Y is nothing but B or L plus effective thickness of the raft. The effective thickness of the raft we already calculated in stage 5. So here it is a 350 mm. 350 mm is nothing but it is calculated from the overall thickness of the raft, which is a 400 mm. Deducting that with the cover for reinforcement as 50 mm. So 400 minus 50 mm is a 350 mm. That was considered here as a T effective. So that effective length parallel to X and Y are 950 mm. L and B are column size and the effective thickness of the slab is a T effective. Now we need to calculate punching shear resistance of slab. For that we need to refer class 6.4 of IS EN 1992 part 1 section 1. On the screen you can see that code. In that page number 99 will explain the punching shear methods to be adopted. So here we need to refer 6.4.3 in order to understand more about the two things. So here there are three important things are given: WRDC and WRDCS, WRD max. These are the three things we need to do while calculating the punching shear check. So here the two checks, major checks to be considered. One is at the column perimeter of the perimeter loaded, the maximum punching shear stress should not exceed it. So this is a major case. It means VED, which is a calculated shear stress, should not exceed VRD max. And VED, In the second case, the punching shear reinforcement is not necessary if VED is less than or equal to VRDC. So now we need to calculate this VRDC and VRDC max and VRDC in order to find out whether the calculated or actual shear stress is less than these two. Means if this is less than these two, means we can say there is no need of shear reinforcement and no need of column or bottom raft sizing is sufficient to hold the punching shear. So let we look into that how to calculate the punching shear resistance of slabs VRD max and VRDC. First we will calculate the punching shear capacity of concrete without reinforcement VRDC. For that, class 6.4.4 of EN 1992 part 1 section 1 and the equation 6.3 N to be referred. For that we need to go to page number 106 and 88. First we will look into that 106. So here that explanation is given VRDC equal to CRDC into K into 100 Pi FCK power 1 by 3 plus K1 sigma Cp, which all these equations should be greater than or equal to V minimum. So this is the equation provided here, and K1 sigma Cp also. So this is the equation here that sigma Cp, if you are considering, this is not applicable for cast at site for normal concrete, because this sigma Cp is a value which we need to derive from the pre-stressing action, so which is not applicable for this concrete. So that explanation for sigma Cp is provided here. So this equation we can still short it out like this value should be 0 and this also should be 0. So only remaining is CRDC, this equation. So let we look into that CRDC. What is a CRDC? So in the same class the CRDC explanation are also provided. This will vary according to the country as per the national annexure, but the recommended value is CRDC is 0.18 divided by gamma C. So that was we had applied here 0.12 divided by gamma C into K, as here mentioned as K, into Pi is a percentage of steel reinforcement, FCK 1 by 3. So up to here the equation is okay, as we had arrived from the class 6.4.4 as defined here. So then what should be the how to calculate the V minimum? So that V minimum explanation also provided here under this note, so which is stating that V minimum is given in expression 6.3N. So for 6.3N we need to refer page number 88 of this code. So here you can see the equation which is mentioned as 0.035 K. This is what we have considered in our equation also. So this equation should be greater than 0.035 K power 3 by 2 into FCK power half. So this is what here. Now our equation is, we have derived the equation from the EN 1992 6.44 class and the equation 6.3N. So now we need to apply these values for this. So 0.18 divided by gamma C, we already seen this value which is derived from table 2.2. For that page number 26 to be referred. So here in the table you can see this persistent and transient condition gamma C can be considered as 1.5. So that was we have considered here, and FCK we know that it is a 30 megapascal, which we have assumed the grade of concrete as C 30 by 37. So accordingly this compression strength of Q or cylinder, compression strength of cylinder to be considered here as a 30 megapascal FCK. So applying all this, we are getting 0.36 as a value. So before that we need to find out the K, how we have arrived the K value. So here that K value definition also given in EN 1992. So again for that we need to refer page number 106. So here it is given as K equal to 1 plus square root of 200 by D. D is the effective depth of a raft, so which should be less than or equal to 2. So that was we have applied here. So the value is 1.76, and for PI or percentage of steel reinforcement, we need to calculate as equal to square root of PIY into PIZ, which should be less than or equal to 0.02. So this PIY and PIZ definition also given. So it means we need to measure the reinforcement factor from slab width, which is equal to the column width plus 3 times effective depth of raft. So this equation B plus 3 into T effective and L plus 3 effective we need to consider up to this. These values are in meter. So this meter span we need to consider how much the reinforcement percentage is required. So for that this is the equation, nothing but it is a by d square by 4 into pt is this length divided by the spacing. So that will give number of rod or actual area of the steel reinforcement which is required for the column location, that divided by this pt, again the length and the effective thickness of the raft, that multiplied by 2 because we are having a 2 layer of reinforcement. So as you can see here in our previous stage video, design of bottom raft, so we are providing both ways reinforcement, top and bottom. So we need to multiply these two reinforcement into 2. The effective section required is 1.65 meter, which we have calculated here. So for this meter of length, for the effective thickness, we need to calculate the reinforcement, which is coming 0.036 as a percentage of steel reinforcement, or the steel reinforcement factor to the concrete. And the similar ways for other side also it is the same value 0.036, and as per the code requirement we need to do this using this formula, square root of PII into PR rho IZ, which should be less than or equal to 0.02. For applying this we are getting 0.036 as a percentage of steel reinforcement. So now we are applying all these values here in this equation. So 0.18 divided by gamma C into K is a 1.76 here into 100 into rho or PI is 0.036 multiplied by FCK is 30 power 1 by 3, which should be greater than. So we are considering the maximum value of both the equation, 0.035 into K value is 1.76 again. So FCK is 30. So applying this we are getting 0.46 megapascal as punching shear capacity of concrete without reinforcement. Next we need to calculate the maximum punching shear carrying capacity of concrete in order to check the control of shear to the concrete. For that class 6.4.4 again we need to mention, we need to refer. So here that the class 4.5 to be referred, and 4.5 notes is explaining the VRD max. So the VRD max anyway it's depend upon the country as per the national annexure, but the recommended is 0.4 times the mu into FCD. So this is the equation given in that, whereas this symbol mu value is given in expression 6.6n. So for that, in order to find that equation 6.6n, we need to refer page number 89. So here you can see this mu is 0.6 times 1 minus FCK divided by 250. So this is what the equation we have arrived, and the value for this is 0.6 into 1 minus FCK is 30 megapascal divided by 250 is 0.528, and applying with this equation, whereas FCD is nothing but it is a 0.85 times FCK divided by the gamma C, which is 3.59 megapascal. So this is what we have calculated as a VRD max. So these two capacity we have calculated. Now next we need to calculate a actual punching shear based upon the sample calculation. We can consider the load case as 31. So 31 load case is nothing but in load combinations. We can see there are a lot of load combinations we have considered. So this 11 to 16 and 21 to 26 are service load combinations, but we need to consider only the ultimate load states combinations, that is 31 to 46. So first for the sample calculation we will consider the 31 load case here in the punching shear calculation. So bending moment for that load calculation is taken from the VLOOK of stability calculation. So this one, so these are the table we have considered. So for that bending moment is a 716 5.4. 0.54 is the bending moment. So that was considered here. My and mx are considered, and also the vertical loads are also considered for the load cases. So these three values we have considered for the sample calculation of punching shear. And the maximum compression force per pedestal is nothing but Vz by 4. So we are dividing the entire load, downward load, for the load case 31 divided by 4. So that will be the vertical force compression plus weight of the column. So here the B and L are the size of the column, and D minus T plus D will be giving the D is the overall depth of the foundation below ground level, which we have calculated here as 2.5 meter. So that is a D. The raft thickness we need to deduct for the in order to calculate the only the column weight. So that T to be deducted from the overall depth, so that we will get this depth of the column. And now we need to add this column length above the finished ground level, so that is plinth level, we need to add it. So then this total length above the raft we need to consider in order to find the weight of the column. So that's what the height here it is considered, D minus T plus D into GC is a concrete specific gravity or density, concrete density, which we have considered here. Dry density we can consider, and here that moment we need to divide it with the lever arm in order to find the tension or compression. So there are two moments you can see on the right hand side picture. So this moment is about X and this moment is about Y. So while this moment is rotating here, there will be two pedestal which is in the opposite side or other side, in the top side are subjected to tension and the bottom side will be subjected to compression in the moment of about y. So this y will cause tension in left side columns and compression in right side columns. So if you are summarize this corner column in the top left will be subjected to only the tension, pure tension, and in the bottom right column will subject to only compression due to this movement. So the effective way is we need to consider the worst loads. So it means the compression which is occurred due to the movement of mx and my we need to consider. So for that we need to divide this entire movement with the lever arm distance. So mx divided by longitudinal spacing and my divided by the transverse spacing we need to apply. So that was this equation. Mx divided by 2 into Cx plus My divided by 2 into Cy. So we are calculating the ultimate loads or compression load which is transferred to the column. So that we can call it as Q. Then we need to find out the soil resistant. Soil resistant is nothing but the number of sites. So here the number of sites we need to consider. So number of column we know that there is a 4 number of column. The 4 number of column should be multiplied with L effective and B effective and multiplied with the maximum compression force per pedestal. So that divided by the overall length and width of the bottom slab, that is B by L, will give you the maximum soil resistance. So that is 6.76. So we need to find out the net punching shear, means we need to deduct this 36.76 to the 178.616. So by deducting that we are getting 141.4 kilonewton. Now we need to apply this 2 times the B effective and the L effective multiplied with the T effective in order to calculate the net punching shear stress. So the Q U net divided by 2 into B effective and T effective, sorry, L effective are here because we are having two side of L and B. So there are four side as it is a square, both L effective and B effective having the same value. So we are applying this four sides strip into the effective thickness in order to calculate the net punching shear. So it is 0.11 megapascal, which is less than the punching shear capacity which we have calculated. So hence no shear reinforcement is required. Similar like this 0.11 megapascal is less than the 3.59. So this way also the maximum punching shear capacity of concrete is okay with that. So with this the sample calculation for punching shear is completed. Now we need to summarize this to the table for all the load cases. So this is what done here. So all the load cases are summarized and we checked for all the load cases whether the reinforcement is required or within the shear limit, and we found it is not required for all the load cases, and also the VRD max also higher than the VED. So likewise for conductor with the deviation also we get checked, that is load case 41 to 46. So this is all about punching shear. Now let me look into that one-way shear check on bottom pad. For that we need to calculate net upward pressure for design. So this we already calculated in the stage 5 for bottom slab design. So here you can see that bottom pad design we have considered this net upward pressure as 176. So you can find those explanation how to find this net upward pressure in stage 5 of this series. Distance of face of pedestal or column from edge of the pad we need to find out. This distance is nothing but here in the picture you can see that in the plan view. So dx is nothing but the face from the face of the column or pedestal, how much the edge distance that we need to calculate. So this we know that the length of the pedestal we can call it as L minus the spacing between these two pedestal and minus this column size or pedestal size whole divided by 2, we will get this dx. Similar like dy also we need to do like that, the entire width minus this spacing minus the column width divided by 2, we will be getting the dy. The same equation is applied here. So L is the overall length of the bottom raft divided by minus cy is a, so here you can see in the foundation and soil parameter. So L by B is a 5 by 3.5 and cy is a center to center distance of pedestal which is 3 meter and cx is a 2 meter. So those we already considered here. So applying this in this equation, we are getting 0.7 meter in x direction and dy is b minus cx minus b divided by 2. We are getting 0.45 meter. Critical section for shear from the face of the pedestal is, so this distance we need to consider from the face of the pedestal how much the critical. So this dx1 is a critical one. So the edge distance is dx, in that we need to deduct this def so that our value is 0.35 meter dx minus dff. Similar like this side in the y direction 0.45 minus T effective is we already calculated here in design of bottom pad, it is 0.35 meter. And SVX is a factored shear force, that is in SLS load combination we have considered. So this one we need to consider per meter. So we are multiplying this SNU into D1X into 1 meter. Similar like for SVY, it is in Y direction maximum shear force also we are doing like that. And the shear strength per meter, we are dividing this into the effective thickness. So this formula is SVX into 1000, we are multiplying because we are converting this kilonewton into Newton, divided by T effective is, we know that it is a 350 mm. So it was in meter, 0.35 meter, so that we are multiplying by 1000 and we are going to design this shear, one-way shear for 1 meter span, so we are multiplying by 1000. So we are getting 0.18 in x direction and 0.06 in y direction. Those values are less than the 0.36 which we have calculated for punching shear. Here this shear capacity we have calculated 0.36 under punching shear calculation. So those are less than that. 0.36 megapascal. Hence, we can call it as no shear reinforcement is required for one-way shear. So this is what the punching and one-way shear calculation. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.